Yeah, students, welcome back to our next session. Today we will see the range sensors. Range sensors. So these are all the topics we have completed so far, and one more topic is lidar. It is a laser type of sensor that we will see in next session. So range sensors, tactile, and we have it can be proximity sensors also. In earlier sessions, we have seen what are tactile sensors, what are proximity sensors, ultrasonic sensors, IR range sensors, infrared range sensors, laser range finders, vision systems. Each varies in complexity, size, weight, expense, accuracy, etc., etc. The detection range is defined as the maximum distance that the sensor can read reliably from. So that is range sensors. So tactile sensors detect distance through physical contact and are usually in the form of one or more bumpers, two or more whiskers. So they are usually set to detect obstacles at or within a fixed distance from the robot. It is in the context of robot we are dealing this. The detection range of bumpers is usually anywhere from 1 millimeter to 2 centimeter. So whiskers have a detection range that varies according to their length, usually placed at the front and extend long enough to ensure safe stopping distance. So in the robot, we have both the bumpers and whiskers. So should extend the entire body width so as to detect successfully any obstacles. So in obstacle avoidance, these tactile sensors are also employed. Tactile sensors have the tremendous advantage over other sensors in that they are simple, provide a binary signal yes or no for obstacle, trustworthy. Simple things rarely break down. So here the disadvantages, they provide only poor or coarse resolution. Bumpers require robot to make solid contact with the obstacles. So dangerous for obstacles and unhealthy for robot. And whiskers can become tangled or caught in cracks. Whiskers oscillate when released after bending, resulting in spurious readings until they settle again. So RF beacons, radio frequency beacons. So radio frequency beacon, these are normally employed for the in between this range 1 meter to 100 meters. So a radio beacon is a transmitter at a known location which transmits a continuous or periodic radio signal with limited information content on a specified radio frequency. Occasionally, the beacon function is combined with some other transmission like telemetry data or meteorological information. So the milliwatt localization system is based on triangulation determination of the position based on distance measurements to known landmarks or beacons. So here GPS is an example of a trilateration system. So the position of a GPS unit on Earth is calculated from distance measurement to satellite in space. Similarly, the milliwatt localization system determines the position of each robot based on the measurements to stationary robots with known positions. So the localization system uses ultrasound pulses to measure the distances between robot and obstacles. Each beacon simultaneously emits a radio frequency pulse and an ultrasonic pulse. So here you can see the transmitter. This is the transmitter. It is the beacon. So this is the team leader. So this is the radio pulse or acoustic pulse, and here you can see the milliwatt. It is the it is the receiver. This becomes the receiver here. So from So from this in terms of time, we have time of flight and radio pulse, and this beacon is actually the Mully-Boat. The Mully-Boat is becoming receiver, and this should be within this range. And now this is the RF beacon to identify by this Mully-Boat, and this beacon acts as the transmitter to recognize an object in front of it. So RF beacons, radio frequency beacon, these are as illustrated in figure. The RF pulse traveling at the speed of light, so that is 3 to the power of 3 into 10 to the power of 8 inches per second, arrives at all receivers almost instantaneously. The ultrasonic pulse, on the other hand, traveling only at 343 inches per second, assuming 20 degrees Celsius air temperature, arrives at the receiver with a delay proportional to its distance to the beacon. So here each milliwatt measures this delay using the RF pulse for synchronization and converts it to a distance measurement by multiplying with the speed of sound. The team leader coordinates the pinging sequences to ensure that beacon signals from multiple robots do not interfere with one another. After all, the beacon's finishing pinging, every milliwatt has a set of distance measurements from its current position to each beacon position. So that is the synchronization. So that is the synchronization between milliwatt and team leader. So this information is sequentially transmitted to the host computer, which determines the actual position of every milliwatt. So in the future, it is planned to calculate the milliwatt positions on the local processor of each milliwatt. However, currently the processor does not have the necessary computation power to perform all these computations. So that is another development that needs to be take place. So RO beacons are in this system, in the same system, what we have seen in that diagram. Each beacon simultaneously emits a radio frequency, RF pulse and an ultrasonic pulse. The RF pulse traveling at the speed arrives at all receivers almost instantaneously. So here the applications of radio beacons, if you see, air and sea navigation, propagation research, robotic mapping, radio frequency identification, near field communication, and indoor guidance as with the real time locating system RTLS, and mapping. We have uses localization is fixed reference frame. It uses the localization in a fixed reference frame. So reflective beacons. So this is beacon based localization, and beacon navigation system are the most common navigation aids on ships and aircrafts as well as on commercial mobile robot systems. Active beacons can be detected reliably and provide accurate positioning information in minimal processing. So it requires very minimal processing. As a result, this approach allows the high sampling rates and yields a high reliability, but it does also incur high cost in installation and maintenance. So that is the drawback here. Most of the beacon based localization systems rely on a set of beacons placed at known positions in the environment. The mobile robot vehicle is equipped with sensors that can observe the beacons, and the navigation system uses these observations and knowledge of the beacon's positions to locate the robot vehicle. So these are all the beacons to identification of the different objects, like what we discussed in earlier slide. So accurate mounting of beacons is required for accurate positioning. Unlike odometry and INS, the accuracy of the localization does not deteriorate with time in a beacon-based system. This is due to the fact that the sensor on the robot vehicle provides observations of position rather than observations of motion, and therefore is not subject to accumulation of integration errors. So here the beacon based localization systems can be categorized according to the type of signal used by the sensor, which relates to the beacon characteristics, and according to the type of information processing employed by the system. The main types of signals used by beacon based localization systems are infrared, laser, ultrasound, and millimeter wave radar. So these are the main types of signals used in beacon based localization systems. So in laser systems, the mobile robot vehicle is equipped with a rotating laser emitter receiver, and the beacons are reflective strips placed at known positions in the environment. The angle of the sensor is registered when a laser reflection is observed, so thus giving a bearing of the observation. Laser is by far the most widespread signal used in beacon based localization systems. The second common signal type is ultrasound. So this system usually relies on active emitting rather than passive reflecting beacons. So passive signals are normally reflecting type and active signals are emitting type. Most objects in typical environments easily reflect ultrasound. Consequently, passive beacons would be difficult to identify using ultrasound. Another advantage of active beacons is that the transmitter signal may contain a specific code to identify the emitting beacon, or the beacons may be identified themselves by transmitting in the laser sequence, with the first beacon emitting modified signal to the others. The third type is signal used beacon based localization system is millimeter wave radar. The MMWR signal is reflected by metallic beacons placed at known locations in the environment, and the radar emitter receiver provides both range and bearing to the beacons. Localization techniques: two main categories of beacon based localization system can be identified according to the type of information processing employed by the system. These are triangulation or trilateration and estimation. So these are the methods used in reflective beacons. Triangulation involves combining several bearing observations to reduce the position of the mobile robot vehicle, using the assumption that position and altitude of the vehicle does not change between the observations. So this is the triangulation method. So trilateration uses the range measurements for the computation of pose of the mobile vehicle. An alternative approach to triangulation is form an estimate of the vehicle pose. Estimation relies on a model of the vehicle and the sensor. The estimate is updated each time a new observation is made. So this is another method, estimate method, and the vehicle is localized from observation to observation using a prediction of the vehicle pose based on the vehicle control inputs as shown in this figure. So here you can see the initialization. So vehicle control inputs to prediction. So prediction is receiving initialization and vehicle control inputs, and the observation is given to update, and it is a closed loop path, and update will be always given to prediction. So this is the reflective beacon. The Kalman filter is widely used to form a probabilistic estimate of the vehicle pose. According to the Bayesian estimation theory, in terms of mean estimate and the covariance of the estimate. So the second one is trilateration. Trilateration is a method to determine the position of an object based on simultaneous range measurements from three stations located at node sites. In trilateration navigation system, these are usually 3 or more transmitters mounted at known locations in the environment and one receiver on the board of the robot. So conversely, there may be one transmitter on board and the receivers are mounted on the walls or rooftop. Using time of flight information, the system computes the distance between the stationary transmitters and the onboard receiver. So this problem has been traditionally solved either by algebraic or numerical methods, and this can be solved using quadratic equations. So here these are the equations, and where here you can see this is the P1, P2, P3, P4, and these are the coordinates, the x1, y1, z1, and similarly it has the coordinates up to x4, y4, and z4, and this is the distance between P4 and P1 is L1, and the distances are given here, the distances between the points, where Pi is xi, yi, ri, I is 1, 2, 3 are coordinates of the station and the range measurement associated with it. The triangulation method to obtain location of a mobile robot P4 from its distance from 3 stations located P1, P2 and P3. In this figure, the segments between stations define the base plane and thin ones those connecting the moving object, and the stations corresponding to the range measurements. Global positioning system is the example of trilateration. So this is a type of GPS only. So this is triangulation. This is triangulation method. So on XY plane, we can see these are the coordinates for x1, y1, x2, y2, and x3, y3. These are connected from this origin, and for each point the angles are measured. So there is theta 1, theta 2, and phi. And triangulation is the most widespread method used to localize a mobile robot vehicle. In this configuration, there are 3 or more active transmitters mounted at known locations, as shown here. The basic triangulation problem of 3 observations. So here, a rotating sensor on board the robot registers the angles at which it sees the transmitter becomes relative to the vehicle's longitudinal axis. From these 3 measurements, the unknown x and y coordinates on the unknown vehicle orientation can be computed. Some cases beacons are not visible in many areas, a problem that particularly grave because at least 3 beacons must be visible for triangulation. Cohen and Casa had the detailed analysis on 3-point triangulation algorithms. The heading of at least 2 of the beacons was required to be greater than 90 degrees, and the angular separation between any pair of beacons was required to be greater than 45 degrees for the efficient computation of algorithms. Because of the technical maturity and commercial availability, optical triangulation systems are widely used in mobile robotics applications. The triangulation typically these systems involve some types of scanning mechanism operating in conjunction with fixed location references strategically placed at predefined locations within the operating environment. A number of variations on this theme are seen in practice. So next is ultrasonic ranging. The sonic, the time of flight measurement, and distance is distance equal to speed of sound into time, and this is one small arrangement of ultrasonic ranging. So here you can see the sensor pulses. The sensor senses sonic pulse signal which is reflected by the object to be detected. From object surface, the ultrasonic signals, the sonic pulse signals will get reflected. The time which the signal requires from the sensor to the object and back is measured and evaluated. The distance is calculated from the time and the pulse speed. Ultrasonic sensors are suitable for use in difficult industrial environments. Disturbances such as dust, soiling, or fog do not influence measurements. Mutually interfering light influences or temperature fluctuations are not a problem either. Because almost every material reflects sonic waves, it uses recommended for level measurements of foils or transparent objects. So here the sonic pulses signal from measurement object and the sonic pulse signal to measurement object. So here the reflections, these are the reflections. The small curves are the reflections. So the classification of ultrasonic sensors: short range distance sensors, displacement precision in the millimeters range. Short range distance sensors are precision instruments which measure optically in a range from 24 millimeters to 700 millimeters using very advanced technology. They measure profiles, diameters, or object thickness, control processes, and handle quality assurance functions in production workflows. They detect the smallest recesses, deviations, or uneven areas even in the range. Short setup times and the simple alignment of short range distance sensors, that is due to innovative teaching reduce facility downtimes and increase their profitability. The extremely high measurement frequencies of the sensors enable high throughput speeds. Short range distance sensors are mainly used in the electronics and automotive industries as well as in the area of robotics. So these are the application areas of short range distance sensors. So the second type is mid-range distance sensors. It provides the solution for measuring ranges from 13 millimeters to 24 meters. Mid-range distance sensors are high-teach measurement instruments for customer requirements in the mid-measuring range. Innovative sensor technologies such as OES3 and time-to-flight measurement enable resolutions down to zero point 0.1 millimeter. Highly precise and reproducible measurements are just as much a matter of course, as is the extremely simple commissioning. Functional teaching, configuring the sensors guarantees shorter mission downtimes. In the development of mid-range distance sensors, value was placed on the consistent implementation of user requirements. Compact designs, a high degree of switching reliability, little maintenance work, and a long operating life ensure optimum use of sensors in almost all areas of industry. So third type is long range distance sensors. So these are ranges from 200 millimeters to 1200 meters. So typical application areas of long range sensors are distance measurement to prevent collisions, detecting small parts at large scanning distances, measuring differences, measuring diameters, measuring gauge heights, positioning parts, etc. etc. These sensors are distinguished by a high degree of dynamic performance and the precision of the device's multifunctional switching inputs and outputs, uh, excellent background suppression as well as user-friendly installation and alignment concepts. Robust designs as well as optionally available accessories ensure reliable use of these sensors even in harsh ambient conditions. So here advantages of ultrasonic range sensors: reliable with good precision, not as prone to outside interference, good maximum range, inexpensive. And disadvantages, if you see, sensitive to smoothness and angle to obstacles, poor resolution, prone to self interference from echoes, cannot detect obstacles too close. So that is the disadvantages, and these are the three ranging sensors we have discussed today. And one more topic left out in this unit is LiDAR, that we will see in next session. We will stop here, students. Thank you.